Hello, everyone. Welcome to the third lecture of our course on heterogeneous systems. And today we are going to start talking about GPU programming, and we are going to talk about what we call the GPU software hierarchy, how the computation is assigned to different threads of execution and how these threads are grouped for more efficient execution and mapping onto the GPU hardware. Remember that regarding the GPU hardware and also the programming model, we were talking about them for both GPUs and also SIMD processors in the previous lecture. Remember that GPUs are basically SIMD engines underneath. For your reference, even though this data map or this floor plan of the NVIDIA H100 GPU looks like pretty homogeneous, we can go into details and the GPU core, and we will find that there are different execution units. And in some sense, this reminds a lot to vector processors and array processors that we explained in the previous lecture. As we can see here, there are units for 32-bit integer computation, 32-bit floating point or 64-bit floating point operation. There are also specialized units for load and store access memory, and there are these specialized tensor cores for neural networks and machine learning. There are also different memory spaces that the GPU cores have access to. Inside each GPU core, we have registers, but we also have an L1 data cache and another memory space, the shared memory that is a scratchpad memory. And then outside of the GPU core, there is an L2 memory and the off-chip DRAM or the global memory. We are going to talk in detail about the GPU memories in our next lecture, but for now, we will talk about the software hierarchy. Remember as well that the GPUs internally execute instructions for warps that are basically SIMD units, and on the pipeline of a GPU core, we have fine-grained multi-threaded execution, which means that in every single cycle, we are fetching instructions or one instruction from a different warp. And this way, the execution of warps is interleaved on the GPU pipeline, and this interleaving and this fine-grained multi-threaded execution enables long latency tolerance. We can hide instructions that take long latency by executing other instructions in the pipeline. As an example of instruction with long latency, we have the accesses to the off-chip memory, for example. But now let's start talking about GPU programming. Remember this slide from a previous lecture where we mentioned, and this we quoted this paper from Fisher in ISCA 1983, where Fisher explains how difficult, or reasons about how difficult it is to program SIMD processors. But GPUs are hopefully easier to program. The rise of general purpose programming for GPUs was more than 1 decade ago, and in some sense it represented the democratization of high performance computing, because for relatively low cost, anyone could have on their commodity PC a powerful GPU with a very high floating point, high throughputing floating point operations per second. And many workloads can benefit from this sort of device, such as matrix computation, image processing, neural networks, etc. But we need to learn to program this system. We need to understand and learn a new programming model, and we also need to understand what are the key bottlenecks when programming this system, and also the ways to alleviate these bottlenecks. Let's start from the beginning. GPU computing basically starts, or heterogeneous computing in systems with GPUs basically starts on the CPU and the CPU memory, the main memory of the system, and there are three main steps. First of all, we need to transfer the input data from the CPU memory to the GPU memory, that is called typically global memory. Then we need to launch the execution of a kernel or the function that is going to run on the GPU. And after this function on this or this kernel completes, the CPU can fetch the results and move them from the GPU memory to the CPU memory. These three steps are represented in the typical program structure in an heterogeneous systems with CPUs and GPUs, where we will normally run sequential or modestly parallel sections of the code on the CPU, while massively parallel sections of the code will run on the GPU. So normally we'll have something like this. First of all, we'll have one single thread or just a few threads running code on the host CPU, and at some point they will offload some computation to the GPU, to the device side. This computation is called a kernel, as I mentioned earlier, is a function that runs on the GPU, on the device, and this kernel uses many a large number of threads. These threads for execution are grouped into sets of threads that are typically called thread blocks in NVIDIA and CUDA terminology. When this kernel finishes, the control returns to the CPU. There will be probably some more sequential or serial execution or modestly parallel execution on the CPU, and then at some point, the CPU may launch another kernel. Remember that programming a GPU uses the single program multiple data programming model, where we typically write code for individual threads, for scalar threads, but these threads will be later grouped into SIMD units that are called warps in NVIDIA terminology and executed onto the GPU cores that are kind of SIMD hardware. In the SPMD programming model, each program or each thread works on different data and can execute the different control flow path, but they can also synchronize. Because the underlying hardware is SIMD, as you can imagine, when we group many of these threads or procedures into the same warp, we want them to do basically the same computation. That could be the most, that would be the fastest execution, because if not, we will have to use predicated execution, we will have to use masks, and we will have to first run part of the computation for some of the threads in the warp, and then for other threads in the warp. That's not ideal. It's doable and it facilitates programming a lot, but at the same time, we have to be conscious about that in order to write more optimized programs. So CUDA and OpenCL are programming models that use SPMD, or also called SIMD, single instruction multiple thread, and they usually they are called bulk synchronous programming frameworks, because the way to synchronize different threads or all threads executing a kernel is terminating a kernel. This is what is called a global or coarse grain synchronization. The host, that is typically a CPU, allocates memory, copies data, and launches kernel. And the device, that is typically the GPU, executes the kernel. How does the kernel execute? So how does the GPU execute the kernels? Well, the GPU runs threads, but these threads are all of them for a single kernel grouped into something called the grid, that in OpenCL is called ND range. And then inside the grid, we have multiple thread blocks, or simply blocks in NVIDIA terminology, in CUDA terminology, workgroups in OpenCL terminology. And all threads that run inside the same block or inside the same thread block can share memory and can synchronize. And the reason for that is that they will execute all inside the same GPU core. And then we have the threads that in OpenCL are called work items. The typical structure of a program in CUDA is something like this. We'll have function prototypes for functions running on the CPU, such as this serial function that we see here in the slide, and there will be kernels, that are the functions that run on the GPU. Observe that the GPU kernels always start with this global qualifier. And then we have the host code, where the execution will start, where the computation will start. And at some point, the host, the CPU, will offload computation to the GPU side. So in the main function of the host, we will first allocate memory on the device, on the GPU, and we are going to use an API called CUDA malloc to do so, where we allocate a certain number of bytes for this pointer DIN. We need to transfer data from the host to the device. So initially, even though we have allocated already some space on the GPU memory, the data initially resides in the GPU memory. So we need to copy from this HIN array to this DIN array. This is a copy from the host to the device. And then we need to define the execution configuration, which is basically the number of blocks in the grid and the number of threads per block. And next, we can call the kernel. That is the moment where we offload the computation to the GPU. In the kernel, we have arguments, and of course, we have the execution configuration that we previously defined. When the kernel terminates, we can transfer results from the CPU, from the GPU memory to the CPU memory. We again use this CUDA main copy operation, but in this case, the destination is H out that is allocated in the CPU memory, and the source of this copy is D out that is allocated in the GPU memory. This sequence of copy, kernel launch, and again, copy back to the CPU can be repeated as needed. For example, in iterative algorithms that call multiple times the same kernel, or simply in other applications where we have multiple kernels offloaded to the GPU. Inside the kernel, we can use automatic variables that are transparently assigned to registers in the GPU cores. We can also use shared memory, that is this shared memory space where all threads running inside the same block in the same GPU core can access, and they can share data using this shared memory space. We will use this shared qualifier to identify those arrays that are allocated in shared memory. And inside the same thread block, threads can also synchronize. It's what we call the intra-block synchronization, and in particular, we use this sync threads instruction. In order to start understanding more about how to program a system with GPUs, we are going to start with a simple code example, a vector addition. This code that you see here is the host code, is a function called backAdd. Assume that this function backAdd is called from the main function of the host CPU. And as you see, first thing that we do in this backAdd function is to allocate GPU memory. We allocate our memory for arrays A and B that are the input arrays, and array C that is the output array. Then we copy data from host to device, as you can see in this parameter here. So we are copying all these bytes from array A that resides in the CPU memory to array A underscore D that resides in the GPU memory. We do the same for array B. Then we will launch the computation on the GPU. This is the kernel call. We are going to see it in detail in a later slide. And finally, when the kernel terminates, we copy the results back from the device memory, from the GPU memory to the host memory or CPU memory. And finally, we can free those memory spaces in the GPU memory. So the vector addition, which is our first programming example here, is as simple as performing the element-wise addition of two arrays. And in the most straightforward implementation, we can just assign one GPU thread to each element in the input and output vectors. So each of these threads is going to be in charge of just one single addition. So it will have to go to memory, read A0, read V0, add them, and then write C0 into memory. So this is the computation done by thread 0, this is by thread 1, and these are for the rest of threads that run on the GPU. This whole set of threads, as I said earlier, is called the grid, but we need a way to assign these threads to the GPU cores. We have a number of GPU cores that, by the way, can vary from GPU to GPU. So what we do is grouping the threads into thread blocks. So these 4 threads are block 0, block 1, block 2, and block 3. And this is the computation done by block 0, by block 1, by block 2, and by block 3. In this toy example, we have just 4 threads per block. Normally, we will have at least 32. That is the warp size on NVIDIA GPUs. And more typically, we will have a multiple of these 32, of this warp size. So how do we launch a grid? First of all, threads in the same grid execute the same function that is known as the kernel, and the grid can be launched by calling a kernel and configuring it with appropriate grid and block sizes. Remember that we need to first define the execution configuration, which is the number of threads per block, 512 in this example, and the total number of blocks. And then we can call the kernel using this line here. So this is what we were missing in our host code example for the vector addition, defining the execution configuration and then launching the kernel with the execution configuration here and the arguments here in parentheses. Now, this is the host code, but what about the GPU code? In the GPU code, we will have something like this. In this case, it's very simple. The vector addition kernel, observe that it's a kernel because it starts with this global qualifier. And here we can see the input array A, input array B, output array C, and the total number of elements. If the total number of elements is a multiple of the block size, we can just write something as simple as this, where for each individual thread, where each thread has its own thread index and each block has its own block index and block size, which is this block dim.x. So for each individual thread, we obtain one index, this I. And using this I, each thread can go to memory, bring the corresponding element from A and B, add them, and store the result in the output array C. If the number of elements is not a multiple of the number of threads per block, then we need to check the boundary condition. So in our kernel code, we will have to add something like this if statement here, where we check if the I is less than n, that is the total number of elements in the array. It's as simple as that. So this is what we call the 1D grid, where the thread blocks are considered to have a single dimension. And because they have a single dimension, then we have this dot x when we define the grid dimension, that is the number of blocks in the grid, and this block dimension, that is the number of threads per block. And similarly, we have block index.x and thread index.x because we are using a single dimension. And we can apply these thread blocks and grids, one-dimensional thread blocks and grid, to also data structures that don't need to be 1D. For example, we could assign different threads and thread blocks to compute on an image that is a 2-dimensional data structure. So as you see, this part of the image is assigned to block 0. This part of the image would be assigned to block 1, this part to block 2, and so on and so forth. And then for each block, we are going to have a number of threads, 4 in this toy example. So in order to access any element in the image, we need to use, as this two-dimensional data structure, we need to use block index, block dimension, and thread index, as you can see. So for example, this element here is the element 25 or pixel 25 of the image, and we calculate that and we obtain the exact address by using the block index, that is 6, the block dimension, that is 4. Remember that we have only 4 threads in this simple example, and thread index equal 1, because this is the bit, the pixel that is assigned to thread 1 in this block 6. But there are also, because they might be more convenient when we have 2 dimensions or 3 dimensions or maybe even more in our data structures. So it makes sense to also use 2D blocks or maybe even 3D blocks and grids. So in the case of 2D blocks, we will have a grid dimension X and a grid dimension Y. As you can see in this toy example is 4 and 4. The value of both grid dim and grid dim X and grid dim Y is 4. And this block here will also have a 2D index. We have block ID x.x and block ID x.y. In this particular, for this particular block, x is 2, y is 1. And then again, we have the same x and y indices for the individual threads in each thread block. And now the way that we calculate the specific position of a pixel in the image is by obtaining its row and column using the corresponding indices and dimensions of block and thread in the y dimension and in the x dimension. For example, the same pixel that we checked earlier in the previous slide, now we see that this pixel is in row 3 and column 1. Okay, so this is all for now. You can read more, you can learn more by going to the book Programming Massively Parallel Processors. Recommended chapters corresponding to this lecture are chapter 1, 2, and 3. But you can also rewatch this lecture, but a longer version of it, if you access the link that is in this slide. In the next lecture, we will continue talking about GPU programming, and we are going to focus this time on the memory hierarchy of the GPU and how its different memory spaces inside the GPU are handled when programming using CUDA or OpenCL, and how threads in different thread blocks can access data in the global memory, the off-chip memory, or threads inside the same thread block can share data using the shared memory. This is all for today. I hope you found the lecture interesting. Thank you very much for your attention, and I hope to see you in our next lecture.